Okay, and we're back. This is example 2, and we've been looking at chapter 3. So this is combining a number of things from chapter 3. Okay, it's just kind of a, we've been adding on to problems. We started out with, okay, if I have a force, what's the stress in a bar? What's the cross section? What's whatever? Then we looked at, okay, well, if I have a strain, okay, or a change in length, and original length, how do I find the strain? And then we put it all together. Okay, so when we look at these problems, we have stress equals E times strain, where stress is force over area and strain is just change in length over length. Okay, so we just use them multiple times. So this is a little bit more complicated, but it's kind of fun, I think. So we have a rigid bar BCD. It's supported by a pin at C and by an aluminum rod at 1. A concentrated load P is applied to the lower end of the aluminum rod at 2, which is attached to the rigid bar at D. The cross-sectional area of each rod is 0.2 inches squared. After the load P is applied, the strain in rod 1 over here is measured at 900 microstrain. Determine the magnitude of load P, the total deflection of point E, the shear force acting on the pin at C, size the pin's diameter given this blah, 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 and calculate the change in diameter of rod 2. That's rod 2. So we have a lot going on here, a lot going on. So the first thing I want to note is this is a rigid bar. So we're going to look at rigid bar rotation. So as I apply a load here, the whole thing is going to rotate, okay, with rigid body rotation, okay? I'm also going to note that we have this aluminum and we're going to have a yield strength. So that's going to be my yield value of stress. We have our modulus of elasticity. We have the shear modulus. We don't need that in here. We have Poisson's ratio. And that looks like everything that we need. So I got this table for you. Normally you would have to look this up yourself. So when I'm dealing with anything in this class, I'm going to have to draw free body diagrams. And so I'm going to draw a free body diagram of equilibrium. So that's kind of like, what we did in statics. Okay. I need to know how my forces are being spread through the system. And so when I do that, then I know that I have a pin here. So I have CY, I have CX, I have tension in cable AB, I have tension in cable DE, I have 30 inches, and I have 20 inches, okay? I also then am going to isolate DE over here, and when I look at that, I can see that the tension in DE has to equal that force P. It's kind of a one-to-one deal. So I now need a relationship between this force P, because as I pull this down, it rotates. We're going to get tension here, so I'm going to have a force in that cable. So I can sum my moments about C. And when I do that, I'm going to have TAB times 20, okay, minus 30 times TDE. And I can cross that off now, and I can call that P because it's a one-to-one ratio. So now I have a relationship between my force P and the force in that cable. So 20 TAB equals 30 times P, and I can write this two ways. I can say that the tension AB equals 1.5 P, or I can say that P equals 2/3 tension in AB. I don't know which way I'm going to be finding it first, but I have this relationship now between this tension and here. And when I sum forces in the y direction, that's when I find that my tension in DE is a one-to-one equivalent. So there's my statics. Okay, I found the relationship now between the force P. I'm going to have to design these as well. So I can sum forces in the x direction. I can sum forces in the y direction. And I will find that CY equals, okay, I'm going to find then that CY equals P, and I'm going to find that CX equals TAB. Okay, so I know this is an example. I've kind of squished it together on your homework. Make sure that you're kind of spreading this out, especially on an exam too, so we can see everything and you have everything. So I now have a relationship, and I guess really I could say that this is CX is 1.5p. That way everything is in terms of p when I find p. Okay. Now I'm going to have a free body diagram, and this one I call deformation. I need to see how the whole system is working together as I load it. So I kind of start out like that. As I load it, I can see it's going to rotate about that pin at C. And when I'm looking at this, I have this cable here. Okay, this cable has an original length of 50 inches, and it's going to stretch. So that's going to be the stretch in cable A to B. When I'm looking here, I have this point D, and point D is going to rotate down to a D prime, but we're not stretching the cable yet. Okay, we're just getting a delta from D to D prime. I know that the relationship is going to be at 30 inches, and then this right here is 20 inches. So when I'm looking at my similar triangles. Now let's look at DE. So if I start out with D to E, okay, we've lowered. Okay, but we're also, when we load this with P, we are going to end up elongating delta of cable DE. Okay, so I have the rotation, how it rotates, and again, I need to find a way to look at the rotation that happens over here, D to D prime, and what happens when I'm looking at B to B prime. And again, I can use similar triangles, just like if it's straight, I know that delta A to B is to 20 inches, as delta D to D prime is to 30 inches, okay? And that's how I can get the relationship between these. I know that this delta is going to kind of come from that force that I've applied that causes the stretch, okay? So now we've got to get started. So these are all my givens. See how they're nice and neat? I have equilibrium relationships. Everything's related to that load P. And then I have deformations. What do I know? I know that the strain in rod 1 measures 900 microstrain. The strain in rod 1, so we know that this strain right here is 900 microstrain. Okay, so if I know this is 900 microstrain, strain is change in length over length, I can calculate delta AB. Once I calculate delta AB, okay, I can also use that material relationship. I can calculate the force that actually caused this amount of change in length. So I can get that tension in AB. And if I can get the tension in AB, I can calculate what is force P, okay? When I get delta AB, I can also then get the rotation, okay, of D to D prime. When I have that force, I can calculate the elongation of this cable or this rod. And so I can find the total displacement of E because it's going to come from not only the rotation, but from the elongation. So I have to know something. And what I was given was the strain. So let's start looking at rod AB. Okay, I know that stress equals E times strain. Stress is force over area. Strain is change in length over length. So when I'm looking at this, I was told strain, okay? Stress equals E times strain. My material has a modulus of elasticity of 10 times 1,000 KSI. So I've got 10 times 10 to the third KSI, okay? My strain was given as 900 microstrain, 900 times 10 to the negative 6 inch per inch. So when I calculate this, I'm going to get the stress from A to B, okay, the stress that's in A to B equals 9 KSI, okay? So remember, this is valid in the elastic region, If we're not in elastic, I will have to go to a stress strain curve. I will have to take this strain, okay? So if we're not elastic, then I would have to go to that strain that's given. That's not going to work there, is it? We're going to have to go to that strain that's given, and I'm going to have to back calculate the stress associated with it, and then I can get the force. So we can note that this 9 KSI is less than, this is less than the yield, which is 40 KSI. So we are in the elastic region, elastic. Okay, so now that I know that the stress of A to B, which is 9 KSI, I know that stress is force in AB divided by area of AB. Okay, I don't know the force in AB, but I do know the area. It was given as 0.2 inches squared. So my units are working out kip per square inch. I'll get kips per square inch. So that force in AB that causes the deformation that results in this strain, okay, see how we're just kind of working backwards there? I get that the force in AB is 1.8 kip, okay? And now I can go back to my equilibrium. If the force in AB is 1.8 kip, I know that P has to equal 2/3 force AB because I have my equilibrium relationships. So the force P that causes all of this is 1.2 kips. Okay, so by working with the strain and understanding this relationship, I was able to go back and calculate the stress, make sure we were inelastic, and then I could calculate the force in the cable. I can use my equilibrium relationship, my statics relationship, and I now calculated that P is equal to 1.2 kip. So I have P equals 1.2 kips. Now I want the total deflection of point E relative to its initial position. So E is starting off kind of like right here, okay? E is going to have to go down the same amount of the rotation that's coming down. So if we rotate down and D came down 2 inches, well, as a result, E is going down 2 inches. E is also changing because as I load this rod, I'm going to have some strain. Okay, I'm going to have a change in length. So when we look at that, we have to understand that that rotational change comes from, okay, it comes from both the rotation and the change in length. So now let's look at deflection of E. Okay, so that total deflection, we're just going to call it a capital E. Okay, that deflection of E has to come from the rotation. So that delta as we go from E to E prime, because we're lowering the whole cable down, plus the change in length of that cable, D to E. Okay, so let's start with this one, delta E to E prime. That's going to come from similar triangles. Okay, that comes from our deformation. This is why you have to have both an equilibrium and a deformation. And I have this relationship right here that delta of A to B, the length of this cable, is to 20 inches. That's our rotational point, as D to D prime is to 30. Okay, so delta from D to D prime equals 30 over 20 delta AB, which we didn't exactly calculate over here, but I know that delta, okay, delta comes from, what is delta? Delta equals strain times original length. I'm just reworking the equation of strain equals change in length over length, and I'm just rewriting it so that we can find delta in terms of that. Okay, so my strain was, what was my strain? 900 microstrain. Okay, so I have 900 times 10 to the negative 6th inch per inch. Okay, times what is the original length of cable AB? It is 50 inches. Okay, so now I can calculate that the change in length from D to D prime equals 0.0675 inches. So that's how much we've rotated down. Okay, that's this part right here. Now we have to find the change in length of the cable. Okay, and change in length then, okay, it's associated with our strain. So strain equals change in length over length. I don't know any of this because we haven't calculated that. So I'm going to have to go back to stress equals E times strain. Okay, stress equals E times strain. Stress is force over area equals E, which is change in length over length. And I am trying to get this delta, the change in that rod, dE. Okay, so from statics, the force in that rod is equal to P. So I have 1.2 kips. Its original cross-sectional area is 0.2 inches squared equals E 10 times 10 to the third KSI. Okay, and then we have delta of DE, that rod, and its original length is, we can look up here, is 100 inches. And so I can calculate that the change in length of that rod is 0.06 inches. So I have my rotation and I have my elongation. So now I can calculate D from E to E prime is going to be the change from D to D prime plus the change in length of the rod. 0.0675 inches plus 0.06 inches. And I get, what do I get? 0.1275 inches, and it's displacing down. There you go. There is our displacement. Okay. Now it says, oh, this is a long problem. The shear force acting on the pin at C. Okay. Well, the shear force acting on the pin at C is going to be the magnitude of Cx and Cy. So from statics, okay, so now we're at C. So from statics or equilibrium, when I sum forces in the x direction, I get that Cx minus, okay, minus that tension in AB, or the force in AB, equals 0. So Cx equals 1.8 kips. When I sum forces in the y direction, Cy minus, okay, Cy minus P equals 0, so Cy equals 1.2 kips. So C has to equal, okay, we have to find the hypotenuse of that vector because these are just the x and y components. So when I do this, I'm going to get that the force that's acting on that pin that at C is 2.16 kips. So the shear force acting across C is 2.16 kips. Okay, so now I have to figure out how to design the pin. Okay, I have to figure out how to design the pin. So if I know that the shear is 2.16 kips, and I was given that my shear yielding is 30,000 psi, that's going to be 30 ksi. Okay, 30 ksi. Then I know that shear equals, or shear stress equals shear force divided by area, and it's a pin, so we're going to have a diameter. So I can rewrite this that 10 ksi equals 2.16 kips divided by pi over 4 diameter of the pin at C squared. And it says back in the problem statement that it is in single shear, so we're not going to do anything with the area. We're going to leave it as such. And I get that the diameter of my pin at C, okay, the diameter of my pin at C has to be at least 0.303 inches in diameter. But the criteria says to round to a nearest quarter inch. Do I round down or do I round up? Okay, this is the minimum diameter I can have. So I have to round up 0.5 inches. Easy peasy. Now it says, so that was DE, it says the change in the diameter of rod 2. We want to find the change in diameter of rod 2. Okay, so this goes back to Poisson's ratio. Poisson's ratio is negative lateral divided by longitudinal. And I know that that's going to be negative lateral. And what is strain? Strain is change in length over length, and that's going to be our longitudinal there on the bottom. So our value of Poisson's ratio is 0.33. So I have 0.33, okay, times our longitudinal strain, which is just change in length over length, change in length over length, change in length 0.06 inches over length 100 inches, negative equals that lateral strain, which is going to come back to our diameter. Okay, remember lateral is cross section here. So that lateral strain is negative 0.0198. And what is, sorry, I'm reusing paper. What is strain? Strain is change in length over length. So we are looking at diameter. Was I given the diameter? Was I given the diameter? I was not, but what was I given? I was given that the original area is 0.2 inches squared. And what is area? If it's a circle, pi over 4d squared. Okay, so I can actually calculate the original diameter. I can calculate the original diameter. And when I do that, I can put that as my length. So I really know that this is going to be the change in my diameter. It's going to be my original diameter value. Okay, original diameter value. And I can find that that original diameter value is 0.505. So we can take this off. We can put 0.505. That's my original. And now I can multiply my original diameter times this negative strain. And I get that delta, my change in diameter, is negative. It's a negative value, right? It's going to be a negative value. And let's see what we have here. So I have 0.0198 times 0.505 equals negative 0.00. We're just going to call that 0.1. So if my original diameter is 0.505 and I'm getting smaller because I'm stretching it, I'm going to subtract off 0.01. 0.505 minus 0.01 equals, and I get a diameter of 0.495 inches, and that's the diameter after we've stretched it out. Okay, so again, these problems I think are really, really fun because I love puzzles. We don't have a lot of equations. You've got to start with equilibrium. You've got to draw deformations, and you have to find the relationship between everything in the problem. Then you have to take what's given. I know the strain. If I know strain and the material, I can calculate all sorts of things, okay? And once I get this, I can go back to my equilibrium and my deformation, and I can quickly figure out everything else that's going on. I can figure out forces, change in length, stress, strain, design my pin. I could, look at the rod, whatever. So it's just a ginormous puzzle, which is kind of fun.